In this final video on time value of money, we're going to look at some complications, if you will, and some more specific kinds of application questions with respect to the time value of money. The first little complication is what we refer to as growth of annuities. Now, a strict definition of an annuity is a fixed cash flow for a certain period of time. Sometimes we may want to determine what would happen if we allow those cash flows to grow at a specific growth rate. An example of this is retirement. You know, you think you're going to get $30,000 in retirement your first year, and your analysis is for $30,000 a year for the rest of your life. Well, if you live from 60 to 90, what will those $30,000 buy in your 90th year? Much less than what they did in your 60th year. So you might want to incorporate in your analysis the growth rate of inflation. So we have two formulas here. One is to insert growth into the present value of an annuity and growth into the future value of an annuity. And of course, you can see that the formulas are massively difficult and complicated. So let's just go to a spreadsheet, right? You determine that you need $25,000 at the beginning of each month for your estimated retirement time of 30 years. You also would like your payments to increase by 3% annually. And if you can earn 8% on your retirement, how much do you need to invest? What is the present value of the annuity to cover that amount? So this is a similar question before, except now we've added the 3% growth. Well, the answer, when you plug this in, right, we know that the payment, you're going to receive $25,000, it's a positive amount. The ordinary annuity, that's an N because we want it at the beginning. Compounding frequency, right? We've asked a question here of monthly, so that's 12. 30 years is time. 8% is the interest rate on the retirement, but the growth of the annuity, we need to plug in here 3%. And the answer that you should get is $4.6 million. Now, the answer from the previous slide with the non-growth was $3.4 million. So you would need to acquire an additional $1.2 million, roughly, in order to keep up with inflation. And likewise with future value of an annuity with growth. If you start investing $500 a month, you expect to retire in 40 years, right? Annually, you expect you're going to get a 4% increase in salary. That will also be adjusted when you invest into the 401k. Assume you can earn 12% on your money. How much will you have when you get to the end of 40 years? So the answer is $500 a month for 40 years with a 4% growth in that per year, earning 12%. That's $8.5 million. Again, it's a rather large amount. Now, if you had the growth number here, right, when you look to the answer, you'll see the present value or the future value of an annuity will have a value. That's the value without growth. And at the bottom, you will see there's the future value of a growth annuity. That's the one that incorporates the 4% change in your investment. Another kind of an annuity is called a perpetuity. And a perpetuity, again, is an annuity. It's an equal cash flow for a certain period of time, but the time frame here is infinity. There is a growth version to this as well. I didn't incorporate that here in our notes, but the basic formula, the present value, you take the cash flow and divide it by the interest rate per year. So here we have an example. Fred Save-A-Lot wishes to endow a chair in finance. It's going to require $200,000 a year to support the chair. And the endowment's going to earn 10% a year. we want to figure out what would happen or how much would Ross need to give the college in order to maintain this $200,000 perpetuity. So if we plug it into the spreadsheet, you can see 10%. There's no number that you put in for infinity, so you just leave it blank. $200,000 is the payment. And you see here that the present value of the perpetuity, they would have to invest $2 million. Well, $2 million, 10% of that is $200,000. So a perpetuity is just an interest-only payment stream. If you wanted to incorporate inflation, plugging in 3% in the cell, we would actually need 2.9 million. But 2.9 million would pay 200,000 this year, 200,000 plus 3% next year, that amount plus 3% next year, and so on. So we'd have a compound growth in cash flow, presumably to keep up with inflation or to try to keep up with inflation. We had talked about compounding frequencies. We know that interest grows faster or values grow faster when we compound more frequently. So we need to have a mechanism to analyze that. So the nominal stated interest rate is the annual interest rate that's charged. But the effective true annual rate, EAR, that is the annual rate that's actually paid or earned. So here we have an example. We have an effective interest rate of 12% on an annually compounded rate. If you plug in 12% in the annual interest rate and the compound frequency is once, you see over here the effective interest rate is 12%. But what if it was compounded monthly? The only thing we need to do is change the compounding frequency from 1 to 12. Then this investment would actually earn 12.683%, or it would pay that 12.683%. So we can look at the impact of compounding through visualizing this effective interest rate. Again, the effective interest rate is the actual interest rate that you pay or earn when we compound differently than annual. We can also solve for returns or solve for growth rates. In this case, we bought an asset for $1,250. It's now worth $3,000, and we bought it 4 years ago. If you leave the interest rate blank, we would solve then the actual return on this investment was 24.47%. If you change the compounding frequency to 12, it would calculate that number assuming a monthly compounding scheme. You can solve for time, right? We invested $1,000, right? We need $2,500 to pay a bill or whatever, and we can earn 8%. How long will it take for our money to double, or go from 1,000 to 2,500? Again, leaving time blank, it solves for the time. It would take 11.9 years for 1,000 to grow to 2,500 if we could earn 8% on our money. Next, there is an approximation formula for this. This is what's referred to as the rule of 72. Basically, it gives us an approximation of how long it takes your money to double. So if you take an interest rate and you divide it into the number 72, that tells you in time how many years it takes your money to double. So if an interest rate is 8%, 8 into 72 is 9. If you actually plug this into the worksheet, the time value worksheet, you would see that it's 9.01 years. So again, it gives us an approximation of how long it takes for money to double. We also have some special applications that have to do with loan amortization and loans. There's a separate worksheet that I provide that's called the Loan Analysis Worksheet. And so loan amortization is the determination of equal payments, and it breaks them down into the part of it that's used to pay the loan and the part of it that's used to pay interest. So this process involves finding what the future payments are going to be and then dividing them and segmenting them, if you will, maybe even decomposing those payments into interest payments and principal payments. So if we go to this worksheet, which is the loan analysis worksheet, here we have a loan of $6,000 at 10%. We're just going to make annual payments to make it a little bit simpler and make it easier to see the worksheet. What will the payments be for a 4-year annuity payment at 10%? So if the interest rate's 10, 4 years, one payment per year, you would make a payment of $1,892 per period. If you made all 4 payments, you'd pay $7,500 on this loan. The loan was $6,000, so the financing costs were $1,571.30. If you scroll on this worksheet, if you scroll to the right, it will take our payments. There are 4 payments of $1,892. We start with a balance of $6,000. 10% of $6,000 is $600. We paid $1,892. $600 was interest. That means $1,292 was the principal reduction. If you subtract $1,292 from $6,000, you get $4,707. 10% of that is $470.72. And likewise, so at the end of 4 payments, the loan has a balance of 0. That is an amortizing loan. So we can divide this loan into interest and principal. The last thing we can look at is we can talk about looking at mixed cash flow streams. So let's assume the corporation wants to do a project, and they have forecasted in the years, for the next 7 years, they're going to invest these cash flows, or these cash flows are going to receive from these cash flows. Interest rates 13%. Now there is a worksheet, it's called the Time Value Mixed Cash Flow Worksheet. You enter the cash flows. We find that the future value of the cash flows is, the future value of the cash flows if they were reinvested is $688,000. If the new line costs, this is the present value. That'll make that a little easier to understand. The present value is $292. If you reinvested them all, it'd be $688. And the question is, if you paid $250,000, would you want to buy this asset? Would you pay $250,000 for something that you thought was worth $292,000? And of course you would. If you did that, the net present value is $42,633. That's the benefit you get above and beyond the cost. Who gets that? It's the person, the corporation here, would receive that extra $42,000. And if we wanted to look at the rate of return, it's called the internal rate of return, you would actually earn 18.61% on this $250,000 investment. So there's lots of examples, lots of ways to, lots of problems for these different types of questions, I guess. For the class, there is a video that describes and talks about each and every one of those. There is a video on solving time value of mixed cash flows, solving loan questions, solving growth questions, return questions. They're all there. There's probably 7 or 8 different videos that will help you analyze and understand more about the problems and what the things are asking for. So that's the end of our video on time value.